Hi, I'm Sebastian from Penn State University. This is Characterization and Testing of Nanotechnology Structures and Materials, ESC 216. Today we'll be talking about basic characterization techniques. So for today's discussion, we will start with an introduction. Then we'll talk about different types of characterization tools, such as optical microscopes, profilometry, ellipsometry, reflective spectroscopy, and then contact angle measurements. Let's start off with a basic definition of metrology. Metrology is a group of processes used to determine physical and chemical properties of the nanoproduct during and or after the fabrication process. Metrology tools are essential to determine the quality of fabrication processes and the resultant materials and devices. Here's a term we should be familiar with as well, yield. Yield is the percentage of quality goods produced out of the total group of goods started. Yield can be enhanced by the ability to measure specific characteristics of a substrate in production. It is used to improve upon manufacturing processes if necessary. In-situ characterization is a key part of manufacturing today. It provides information about the quality of a device before it's completed. This can improve yield, minimize waste, monitor processes, and provide data for statistical process control. This process is often non-invasive. In-situ characterization tools basically is talking about the use of characterization tools in line. It's used to gauge the progress of a manufacturing process, and it's designed to not interfere too much with normal production flow. So what can be measured in situ? How can we do this? Well, we can measure things such as substrate temperature, surface quality, film thickness, growth or etch rates, optical constants, residual gases, and others. Here is an example. This is the graph from an RGA, a residual gas analyzer. And we see on the left, we see pressure. On the bottom, we see AMUs, or atomic mass units. So we're looking at different elements which are present in the sample. And the pressure can kind of give us an idea of the percent composition of the residual gas. Here is an example showing residual helium at about 1 × 10⁻⁴ torr system pressure. This is actually an example of a leak test. So what you do is if you think you're experiencing a leak but you can't find it, you can basically set up your helium tank, spray a little bit of helium in around different areas on your setup, and once you see a helium spike on your RGA, then you know you've found the faulty gasket or valve, etc. So that was in-situ characterization. Now let's talk about ex-situ characterization. So X, now we're outside. Okay, this is characterization that necessitates taking a product out of the production line for testing and characterization. So there are several reasons for performing certain characterization techniques ex situ. These may be invasive, they may require special sample prep, and they may be low throughput. So basically whether or not a characterization method is performed in or ex situ depends on the production process, and therefore will vary from process to process. So a couple types of common ex-situ characterization techniques are shown below. So for structural characterization, we could do X-ray diffraction or X-ray photoelectron spectroscopy, Auger electron spectroscopy, and secondary ion mass spectroscopy, or SIMS. Some common examples of ex-situ microscopy include TEM, AFM, and SEM. So transmission electron microscopy, scanning probe microscopy, and scanning electron microscopy. All examples of ex-situ microscopy. Okay, so that's it for our introduction. Now let's go ahead and look at some of these characterization tools. Our first one up for discussion is optical microscopes. In optical microscopy, it's what you think of when you think about a microscope. It's the oldest type of microscope. It uses visible light and a system of lenses to simply magnify an object and produce a larger image. Due to the size of the wavelength, however, only low magnification views and pictures around 1,000 times magnification are possible. Some light microscopes can be connected to cameras and computers, and this provides simple and cost-effective defect detection. So here's a basic setup for two forms of optical microscopy. On the left, we see the setup for bright field imaging, where we have a light source coming in on the right side. We use a two-way mirror. Light passes through a lens, hits our sample, bounces back up, passes through the two-way mirror, and then we have several viewing optics where we would position our eyes or a camera if it were sent to the computer. On the right, we see an example of dark field imaging. We still have our viewing optics towards the top, but now we see a very different type of picture, and let's assume we're looking at our same sample here. What we do is we position our light source towards the bottom and at a very low angle under the lens. Okay, then basically the light that scatters back up through the lens, which is reflected only by or primarily by surface irregularities. That's all the light that reaches our viewing optics. So this is great for viewing irregularities or surface defects. Here's a kind of more complicated diagram on the left, and then a picture of a typical optical microscope on the right. This microscope is in our lab. It's a Leitz Ergolux, and the optical microscope has video and still camera CCD attachments. So here are some specifications. I'll just pick out maybe some important points. Like we said, a CCD camera. The advantages are that we're able to view a variety of samples, and there are bright field and dark field modes which you can quickly switch between. Some of the disadvantages, like we said, are pretty significantly limited magnification range, especially compared to other characterization tools. And then the imaging software does require manual adjustment. So also, it's, as far as advantages goes, it's easy to use, and we can capture images with the camera and therefore saving the computer. Another disadvantage is, though, we can't measure depth at all. So we cannot use these scopes to measure feature depth on a substrate. Now let's turn to profilometry, a unique, different type of characterization tool. So profilometry uses a sharp probe and physically contacts the surface of a substrate to determine the topography of the substrate. It can be used to measure film thickness, surface topography, as well as step heights. So here's an image of a typical profilometry scan, and the font's kind of small, but what you should see is this general, a step, then like a kind of a ravine, another plateau, then a deep, wider pit, a spike, and then a low point. What you're seeing here is just kind of a side profile view of a line topographic scan. So this scans in one straight line, and you're seeing the height of the sample as it's scanned from left to right. In this example graph, the height scale is dramatically different than the length scale. So that's typical. These scales are not the same. It might only be, let's say, hundreds of nanometers tall, while the scan might be several tens of microns long. So that's typical for showing you feature heights, step heights, and different things of that nature. Here's an example of a desktop profilometer. This is a 10-core 500 alpha step profilometer. You can see it looks like a kind of a computer up top. You have your keyboard, so that's your interface, and then you would put your substrate, let's say a wafer with features on it, on that kind of large black stage. Then there's a small needle or probe which kind of drags across the surface and gives you the profile. Hence the name profilometer. Here's a picture of a Veeco Dektak 6 profilometer. I guess the most prominent thing here is actually a optical microscope kind of coming in from the top right there. And that's just so you can kind of have a visual, you can align or put your sample where you want to under that tip before you lower the tip. So before you lower the tip, you can kind of line it up so that you actually take a measurement of something you're interested in. Kind of makes sense there. And then on the right, we have some more detailed specifications on the Veeco Dektak, which you can pause if you're more interested in. Okay, our next tool will be the ellipsometer, and therefore the characterization technique is ellipsometry. Ellipsometry is a measurement technique that uses the polarization of laser light to determine film thickness. It's a non-destructive and non-contact technique. So it's very useful. It's a great method for measuring thickness of materials that are transparent. Ellipsometry uses a linearly polarized laser light source that when reflected from the sample becomes elliptically polarized. So it's linearly polarized on its way in, then after reflection from the sample, it's elliptically polarized. Polarized light is light that consists of only light rays traveling in one plane. So what happens is the shape of the reflected ellipse is measured, okay, by a detector, and therefore the film thickness can be determined based on certain given information, whether that's the angle, so the angle with which you set up your laser and detector, that'll be the angle of reflection, or perhaps you know the index of refraction of the material you're working with, and then you can conclude its thickness. Here is an example of a variable angle spectroscopic ellipsometer. It's a Gartner Scientific. In the image on the right, you see again you have kind of a computer interface. On the left is a large laser. You see a center stage, and then the detector is on the right. This machine is able to vary the angle of incident light, and this helps us optimize images. Basically, you take two measurements from two different angles. It helps you get a more precise, I guess, result from your analysis. If we look at the diagram on the bottom, we see how the basic setup is your laser light source. You have a polarizer, a compensator, then it interacts with the film. Remember, it has to be a transparent film on your substrate, and then it's analyzed, goes into a microscope, and kind of camera detection scheme. Again, if you know the index of refraction of your material, you can come up with the thickness after using this tool, or if you have a good idea of the thickness, you can conclude the index of refraction and therefore the type of material you're working with if it's unknown. So here are some more details about an example Gartner ellipsometer. Just some things, I guess, that may be significant are film thickness range, 0 up to 6,000 nanometers, so that's pretty large. The accuracy and repeatability are very nice, plus or minus 3 and plus or minus 1 angstrom. That's about it. If you want to know more about it, you can obviously pause the video and read more, but those are kind of the highlights there. Then if you're interested, the laser light source on this one is a 630 nanometer helium neon red laser. So again, we talked about refractive index. If you're not really aware of what that is, well, it has to do with it's the property of a transparent substance, and it addresses how much a light beam bends as it travels through the test media. So just to tell you a story, if you've ever cleaned a pool with a brush on the end of a long pole, or maybe a little vacuum on the end of a long pole, the pole looks like it's bent once it hits the water. And we know it's not, because when you take it back out, it's still straight. The reason it looks like it's bent is because the density of water is different from the density of air. Air and water are both transparent substances, but they have different densities, and because of that, light travels at different speeds through those two materials. And when light enters a material of higher density, it's bent. Okay? And it's bent at a certain angle, and it has to do with the density of those two materials. And the refractive index basically kind of describes the density, but more accurately describes the speed of light through that material. So the way that the ellipsometer works is by measuring two unique angles of incidence, it determines the index of refraction and or the thickness of your test material. And the changes in index of refraction can represent changes in stoichiometry of your material as well. So here's an example, just like the story I told, where you see light entering air, which has an index refraction of 1, and then it is bent towards the normal line as it enters silicon dioxide, where it has a higher index of refraction. And the bottom figure, if it's leaving silicon dioxide and going into air, it'll actually bend away from the normal. And this is always the case, that light will bend towards the normal when entering a higher density material, and it'll bend away from the normal when entering a lower density material. Okay, up next for our characterization tool is reflective spectroscopy. Reflection spectroscopy, or reflective spectroscopy, is the analysis of light that has been reflected or scattered from a solid, liquid, or gaseous medium. It's commonly used to determine film thickness and or index of refraction, much like an ellipsometer. It's non-destructive and non-contact. It's also simple and can be operated at a relatively low cost. So in reflection spectroscopy, you see our basic setup there where we have our light source and detector basically at the same location, are sampled down below. The way it works is a broadband light source is reflected off of the sample at normal incidence. That means the light basically goes straight down, bounces straight back up, and hits a detector. The intensity of the reflected light is measured over a large range of wavelengths. And then computer software will utilize the properties of dispersion, okay, which again is the wavelength dependence of a medium's index of refraction, to determine the film thickness. So it still has to do with the index of refraction and bending of light, but instead of being bent because of the different densities and having to do with the different incident angles, it makes use of the fact that different wavelengths of light actually kind of bend differently. It's called dispersion. Okay, so different wavelengths, i.e., different colors of light, and it will go through a whole gamut of wavelengths, will have different ways that it interacts with the material. And this can give us information about either the index of refraction, the type of material, or the thickness of the material, if we know indeed what that material is. Here's a reflection spectroscope. This happens to be a Nanometrics NanoSpec AFT, and we see the basic setup over on the left, where we have a light source, a beam splitter, so light comes down, interacts with a objective where it's focused down to the sample. Part of the beam goes directly up without interacting with the sample. And basically those two beams are basically the cooled CCD array, and then your kind of computer and whatnot compares the two. It compares the incident source as it is beam split and travels directly to the detector, and it compares that with the light coming from the sample. And then, of course, it compares those differences over the whole range of wavelengths. As far as advantages and disadvantages, reflection spectroscopes are able to analyze multi-layer films. They can measure organic films like photoresist. But they usually require a reference sample of known composition and thickness. So, that's somewhat of a disadvantage. You have to have a known reference sample in order to compare it to your unknown. Okay, so the last type of characterization tool or technique we're going to discuss is that of contact angle measurement. So contact angle basically measures the adhesion of liquids to a surface, and it can be used to calculate the surface energies or adhesion tension of a material. This characterizes surface parameters. Okay, this is sometimes known as the wettability or hydrophobicity, cleanliness, finish, and adhesion. These are all different parameters or surface parameters which can be characterized using a simple contact angle measurement. These parameters can be used to predict things such as adhesion, corrosion, and also biocompatibility of materials, which is very important whenever introducing kind of foreign materials into a living thing. So instruments that analyze contact angles are either referred to as tensiometers, contact angle analyzers, or goniometers. The way it works is the tangent angle formed between a liquid drop and its supporting surface is relative to the forces at the liquid-solid or liquid-liquid interface. So what that tells us is this angle here, and if you look at the little diagram, you see that contact angle is actually representative of surface bonding energy. Believe it or not then, simply by measuring that contact angle between the droplet and the substrate below, we get information about the surface bonding going on between that material and the substrate. So here are a couple different contact angle tools. On the left, there's a Crust DSA contact angle analyzer. On the right, there's a Radian DCA analyzer. And below, there's a Sensodyne bubble tensiometer. These are all different types of tools and the way they're set up, but they're designed to do the same thing, to measure the contact angle and tell us about the surface energies of a substance reacting or interacting with another material below it. So this is one example of where contact angle was important. It's a case study in biological applications where they were studying the surface functionalization of amorphous silicon and silicon suboxides for biological applications. Again, we said contact angle measurements can be very important for different reasons, and one critical example is for the biocompatibility of materials in the living organisms. Here we see some information from that study. The wetting angle for 4 different silicon and suboxide samples was measured as a function of surface treatment with HF. Turns out that the longer the 4 samples were treated with HF, the more the surface topography changed and the smaller the contact angle became. So as the treatment with HF increased, the contact angle decreased, meaning there was a closer interaction, okay, between the droplet and the substrate below.